Welcome to ST&G USA Corporation's material selection for prosthetic socket fabrication. This toe is very interesting. It's not laminated, but it's made of wood. And if you notice, it has different panels on it that provided some movement, but also increased balance. There were signs of adjustment by whoever made it to provide more comfort to the wearer. You can see that there is a variety of different types of sockets and setups that are used. So when we look at the different types, we can assume that we will not use the same layup for every different socket that is out there because they require different functions. They require different parameters as far as what they're doing. Some weight bearing on the top, we have some weight bearing on the bottom, on the prosthesis on the left, and we have some joints on it. So we do have a lot of stress that's going to occur on the joints on the bottom section. It's going to want to pull out. There's a lot of compression and tension occurring while they're walking. So as we look at socket number 2, there's a big flexion contracture, which is accommodated by an offset plate. So there's a lot of stress occurring on that plate and on that socket attachment. As we look at the socket towards the middle, we can see that there's an adjustment on it. There's a dial that can increase tension or decrease tension on that string mechanism. And what that does is it will tighten up the top portion around the brim. Even though we do need support, we do want it stiff, but we also want it flexible enough where it can respond to this tightening of the tension. If it's too stiff, then it can fatigue this mechanism prematurely and make it fail. Now, if we look at this white socket, the fourth one from the left, we have a suction socket. There are no windows on it. There's no adjustment on it. It's just a straightforward socket that's attached to the top of a knee. To the right, we have this elevated vacuum socket. How we approach that is going to be different than the other sockets because we want to maintain an elevated vacuum environment. So we need to be sure that there are no air leaks, there are no voids, because what will happen is you will lose your vacuum. Now, if we keep going to the right, we have this typical BK with pin lock. So we have a lot going on here because now we have a mechanism on the bottom. We want to mount it 4-hole. So we have a big void in this socket. We want to make sure that it doesn't crush, it doesn't push through, it doesn't pull out. And also when they're walking, we want to make sure that it stays stable. So there's a lot of variations in all these different sockets we want to keep in mind when we're trying to fabricate it. Now, a long time ago, there used to be metal sockets. So you can imagine it takes quite a bit of talent to make one of these sockets. Not only do you have to shape it, you have to smoothen it out, because if you look at the picture in the middle, you can see where it's been hammered, and now it's on this English wheel to smoothen all the hammer marks out. So there's a lot of talent and art involved in making one of these. It's also, if you think about it, pretty time consuming. So if we look at the far left, we can see how it's all integrated, where they actually have a shin section that's also made out of the similar aluminum or metal, depending on what they were using. And then we have these adapters that are attached to the socket, and then there's another adapter that's attached to the knee joint. So it kind of helps to blend it in from the different shapes and sizes. And these are probably individually made as well. So if we look at the far right picture, this is actually a current prosthesis. You can see what goes into this prosthesis from that cast. This prosthesis is actually made out of aluminum, and I had the opportunity to actually look at this and handle it. I was surprised at how light this prosthesis was. This, again, if you look at the contours of what it has to fit, That's going to take some time to make that socket. As we get into laminating sockets, we can accommodate some of these more complex shapes, more complex type of prosthesis more readily and repeat it. Because if the person making these sockets were to retire, unless you have an apprentice or someone that's been trained, you're not going to be able to make another socket like this. Let's look at leather sockets. Leather sockets are very interesting. This also takes a lot of talent to make. Now, these particular sockets were made out of one piece of leather. So these were stretched, formed, and as you can see on the left, finished out of leather. So the interesting thing is we normally make sockets that are rigid. Yet here we have examples that are still being used today of sockets made out of leather that are more flexible. Sure, they're attached to metal joints, but we still have, for the most part, a flexible socket. So this starts a big debate, which we have seen in many meetings, on some people who want a very rigid socket. There's also the other extreme where people want sockets to be more flexible and dynamic. And then you have the ones in the middle who like some rigidity, but also some flexibility. So as we look at this needless or tick socket on the left and in the center, we can see that there's a lot of static load because of how the lacing is. So as it gets tightened up, you're going to get that hydrostatic suspension, but you're also going to get some end bearing within the socket. And then you have your medial lateral stability from the knee joints. So there's a lot of stress occurring from those knee joints onto the mount, onto the shin section. As we look at the signs, we can see that that is all leather. We have a foot filler underneath. And it's incredibly well made. This leather, they start off with is 6 millimeters or about 1/4 of an inch thick. And they soak it and then they stretch it. There's a lot of hours that goes into this. Just like with the metal, if you have one of these technicians who decide to retire, if there's no apprentice or someone who doesn't have the same amount of working knowledge or hand skills to do this, then it will be lost. So that's where we have the laminated sockets. There are more people who are able to do a laminated socket than a metal socket or a leather socket. So nowadays, we're looking at composite laminates. We have sockets that are made out of resins and fibrous materials. And what constitutes a composite laminate? Well, you have layers of fibrous materials that are joined together. What we like to look at as far as properties are in-plane stiffness, bending stiffness, and strength. We do need stiffness to support the body, but we also do need some designed elements in there where it does give a little bit, because if it's totally stiff, sometimes it's not comfortable. So we need to look at how we apply these materials within a matrix and with the fibers. Plywood is a perfect example of a composite laminate. If we look at the wood grains, we can see that they run in different directions or different layers, and it's held together by a matrix, which is the glue. So we have the wood, that's fibrous material. We have the glue, which is the matrix. We have the design elements in place, which is in-plane stiffness, and it meets some of the criteria. This material we would use for different applications, such as building a house or flooring. So let's look at a matrix. What is a matrix? One of the definitions I found of matrix is something within that takes form. If we think of resins that we're using, it starts off as a liquid. And as it starts to react, starts to gel, and then it hardens and it takes that form that we're laminating. So what we usually do with the vacuum infused polymer resins that we're using, what we try to do is have a good resin to fiber ratio. If we have too much resin, then that part could be too heavy for one, and for number two, could be too brittle. Because if you have too much resin, the resin will tend to crack. It will not be strong enough to resist the cracking. So what we're looking at is trying to have some kind of a ratio. A ballpark ratio is 60% fiber to 40% resin. This can depend on the resin you're using, the type of fiber, what you're making, but a ballpark just to think about is 60% to 40%. Why? Well, this is pretty close to the sweet spot of having good fiber that's reinforced by the resin. And as the resin sets, we don't have too many voids of excess resin. So the strength of the laminate is dependent upon this ratio. If we have too much fiber, say you have 90% fiber and 10% resin, well, something's going to happen because now you have too much fiber. It's not going to be able to be held together adequately with the resin if you only have 10%. So as we talk about the matrix, which is resin, and as we go left to right in that list, we're also going from the weakest to the strongest. So if you're still using a polyester-based resin, it's not going to be as strong as if you're using an acrylic-based resin or an epoxy-based resin. But one of the problems with polyester resin is that it is UV sensitive, and it also is not the strongest resin you can get. So let's look at an example of fiber with a liquid matrix, and that's an adobe brick. You have fiber and mud, and you mix it all together, you put it in this form, and now you have a brick. Now, if we look at some of these resins that are readily available, we have a big variety. Epoxy acrylic, composite matrix blend, orthocryl lemon hearts, it's 80/20. We have this epoxy resin from fiberglass, and then we have ER resin. These resins, you need to mix a part B, and then we get a reaction. So the 80/20 in particular, so acrylic resin, it's 20% flexible. So you can see there's a choice in different types of resins. Polyester resin is probably the lowest strength resin available. It will have issues bonding carbon because carbon is coated with epoxy, which we call sizing. And the issue is polyester can have issues sticking to it because when we laminate, we're not laminating to the carbon fiber, we're actually laminating to whatever is coated on the carbon fiber. The other issue with polyester resin is the outgassing. The outgassing is very toxic. One of the ways to find out what type of resin you're using is to look and see what the ingredients are. So for example, polyester resin usually has a styrene base, and that's how you could tell what type of resin you're using. So it's generally not recommended for using with structural applications with carbon or aramid fibers. So this was one label from a MSDS sheet, and it has a warning on it. And it does state that there is styrene if you look at the red circle. It has a warning that says this product can expose you to chemicals including styrene, which is known to the state of California to cause cancer. So if you like to use polyester resin and it does have a known toxic agent in it, I guess that's up to you. But for me, I like my health, so that's why I myself am diligent in checking the MSDS sheets. Make sure that you have a decent resin that you're using. Acrylic resins does not have styrene. So acrylic resin in general is relatively safe to use. Carbonic acryl is a thinner blend, so it helps to saturate through carbon fibers with the coating. Acrylic, on the other hand, is a little thicker, so sometimes it does not saturate as well. Around the world, acrylic is the favorite resin of choice. The one issue with acrylic is the hazardous shipping charge because of the partner. So some of the things about acrylic resin, when you get the can, before you pour it out, be sure you shake and mix the can because it does tend to separate within the can, especially if it's sitting. Because if you do not, you're going to get different ratios of the acrylic resin. Some may be more at the bottom, some may be more at the top, and this can affect the outcome. For example, curing rate, the gel time, if you get bubbles or not, how hot it goes off. So make sure it's mixed depending on how long it's been sitting, regardless of what acrylic resin you have. So again, you have your typical 80/20, and then you have your carbon acrylic resin. In general, acrylic resin is very sensitive to the ratio that you mix it. You want to be sure that you stick around a 2% hardener. If you go under or over, it could affect how the socket comes out. Also, it could affect if you get bubbles or if it also gets very hot during the hardening process. So you don't want to compromise your lamination. Make sure you measure all this out. Be as accurate as you can, because 2% to 3% is not a big difference. Again, 80-20 has 20% flexible mixed into it. There is pure acrylic resin, but it's probably not as forgiving as the 80-20. Carbonacryl in general is less viscous, and it's a special blend to help saturate into the carbon fiber as far as working itself into, for example, like a braid. So if you have a 12K braid, you have more fibers that you have to saturate into with the resin. Now you're actually saturating into what the sizing or the coating, not the actual carbon fibers. The more fibers you have to deal with, it's better to have something a little more that can flow, that is less viscous. So that's why you have carbonacryl. Now also with the pigment, you want to make sure that your pigment is mixed appropriately as well. If you go too much, it can actually soften your socket. Pigment is a resin softener. So in general, just be aware of the manufacturer's recommendation for mixing all your resins and be as accurate as possible. Measure it out. Make sure that your equipment is clean so that you don't get a false reading. Now, as we get into epoxy resins, epoxy itself is not as harmful as, say, the hardener is. That is the part B of the epoxy, because usually the hardener is corrosive. Now, the ER resin, for example, is touted as being safe to ship. And the nice thing about it is the cleanup. You can use soap and water, and also what you're going to be exposed to and what some of the harmful elements are, if there are any. In general, you can see that we're going over the contents of some of these resins. You want to make sure that you do read the MSDS, because you want to be, in the end, you want to be safe. So why are we covering all these resins? Acrylic, polyester, epoxy. In general, epoxy is a stronger resin to use, regardless of the material that you're using. Now, one of the downfalls with epoxy, and most of you may be aware of this already, is the longer hardening time. It does take longer for it to start to gel and harden. So you can possibly get it done quicker. Also with a better socket as far as the integrity with the strength, and that is to heat cycle it. Something that you can look into with some of these resin manufacturers is check their website and look and see what they offer as far as enhancing the workability of their product. Now, the one nice thing with the ER resin, and I don't know how this pertains to some of the other epoxies, is that you can actually do a post-heat modification if necessary. For example, polypropylene, you can heat up a big area and do a small general adjustment. You can do that as well with the ER resin, and that's one of the things that they tout. Now, trying to heat modify carbon, usually as soon as you start to heat up carbon, it starts to delaminate already, even before you even push on it. So I would still be careful if you're laminating carbon and you want to do some heat modification to it. Now, as we look at some of the materials that's available, just looking at stockinette, braids, and tape, as we look at the stockinettes, there's cotton, there's nylon, and there's niglass, which is basically a blend of nylon and fiberglass. The nice thing I like about niglass is you're getting more benefit out of using this blend, because it enhances the strength over just nylon. Nylon will still deflect. It will not give you as much strength as a niglass. And then if we look at cotton, I've seen people use cotton stockinette within their laminations. And to me, cotton wouldn't be my first choice, because it's basically going to absorb all the resin. It's going to make your socket very heavy. It's going to swell, and you don't get as much strength out of it as you would, say, a nylon or even the niglass. Now, if we look at braids, there's a lot of different braids available. I've seen hemp braid. There's fiberglass braid. Fiberglass braid is sort of heavy, and it's actually pretty soft after it's laminated. And then you have your carbon braid, which we're all used to. Carbon in general, when you laminate it, it usually is stiff. Trying to vary the stiffness with carbon is very difficult. Then you have NSP, and we'll go into that material. And then we have a Paralex. Paralex is a carbon NSP blend. Carbon and fiberglass is another blend. And then you have your carbon Kevlar. Now with the tape, you have fiberglass tape, carbon tape, and you have NSP tape. Depending on what material you're looking at and what resin you have, you could have issues with compatibility. So if you're using a polyester-based resin, you're going to have definite issues with a carbon Kevlar type braid because Kevlar carbon with the polyester doesn't bond very well. So let's talk about thickness of a lamination. And when we go around to different places around the world and we ask, what do they use typically? The answer usually is we have no standard. So I would say globally there is no standard. There are some references to some layups. Some seem rather thin. If you look at this one, we could say that it looks rather thick. There's a lot of layers of stockinette being used here. If we look really deep into it, it looks like it could be a nylon stockinette. Now, one of the issues with this is you have a lot of resin that you're using that's filling in the voids of this stockinette. So it's going to make this socket really heavy, which it was. And this is a little BK, and it was pretty heavy for the size. And if we look at the thickness, it doesn't necessarily mean it's going to have good longevity. Will it be stiff? It was not as stiff as it could be. The other thing that we look at, if you look at the picture on the left and you look at the shelf, the popliteal shelf of it, you can see that there's some discoloration. It actually has some saturation issues because of the thickness of the amount of the material. Also, if you look way in the bottom of the socket, you can see that the component that they laminated in is starting to actually push through to the surface of the socket. It hasn't even been worn yet. So now you have issues with, you may not have enough material at the bottom of the socket to prevent this component to push through and make the socket fail, which I've seen happen before on other sockets. And yet you still have this thick, heavy socket, and it's not as stiff as it could be. So the whole issue is making it thicker just to be stiffer. Is that better? And do you really get a stiffer socket this way? You definitely get a heavier socket this way. And these are some of the things we can start discussing and think about when we have a prosthesis that we want to make and look at how we want to design it. Now, another thing that I've seen, I've been to some shops around the world and I asked them, what materials are they using? And so they say, oh, I have some carbon. And when I say, oh, okay, where is it? Because I usually don't see the materials out. Sometimes they'll pull out a weave that they have that's just a flat sheet. It's not a braid. If we're making these cylindrical parts, especially with complex contours like the one on the left or the one on the right, the weave usually will not be as good as a braid to lay on the surface that we're trying to make. Now, there are some weaves that can conform, but then you have to cut the weave, you have to lay it on, and then have it overlap. So now, are you putting the fibers in the correct orientation? You have the fibers in the best placement possible. There's some papers online that state that you have to have the weave in the direction of the line of progression. So if you have a flat weave and not a braid, are you going to be able to put this placement of the fiber orientation in the correct plane that you want? Usually, what I've seen as far as with a weave, most weaves are used for a flatter, wider surface. For example, like a door panel, a hood, or a fender. And a braid is usually used for something that's long and tubular, similar to what we do, which is a limb. We have a segment that is either conical, they're tubular, for example, like the figure on the right. That would do well with a braid. For what we do in general, you do want to use the right material. Usually you're going to want to use a braid. A weave would be, if you're doing maybe a window, you can use a weave there. But still, if you're trying to do a window on the prosthesis on the left, you're going to have a hard time getting that weave to lay perfectly where you want it. Now, we've all been under a time crunch. We've all had many projects to do. And you can see here, this has 8 stations, and there's one technician running all 8 stations. At the end of the year, the end of the month, all these projects come in. He's going to put them in the station and try to get them done as quickly as he can. Now, given that situation, would he be able to lay up and apply the materials correctly for that given project? In reality, most of the time, they're just going to put on whatever they can with the same type of layup that they normally do, and they will do it for whatever project comes in. Some thought would probably go into most of the projects that they're doing, but in general, most places do the same type of layup for a given range of patients, say for a below-the-knee prosthesis. There's a given formula that they'll use for a wide range of patients and activities with a standard layup. Now, is this the best way? Most of the time, you might get by, but it's good to start thinking about how to approach how we lay up and use fibers more efficiently so that we get the best performing prosthesis that we can. What are we trying to achieve? Do we have a very high impact prosthesis like the one on the right? Or are we trying to fit an elephant? There are so many variables that we have to take into consideration. Activity level, weight, the level of amputation, what kind of components we're using, what kind of environment, how active are they? Are they mobile? Are they able to use your hand? So there's a lot of things to take into consideration. And given time, sometimes we're in a time crunch and we just try to do things the same. Sometimes we can, and sometimes we can't. Now let's look at what is actually happening to the socket when the prosthesis is being worn and they're walking. Now let's look at one phase of the gait cycle, not the whole gait cycle, but one phase. And this is just in the single limb support. You can see on the left, they're balancing themselves on the prosthesis. So if we look at their center of gravity, basically this light blue line where their belly button is, that's usually where your center of gravity is. We can see that it's starting to shift over. And in the process of shifting over, you're going to get this lateral shift to help try to counterbalance the limb inside of the socket. And some of that is just how we're trying to compensate. So as we start to shift over and we get this lateral shift, we're getting a lot of force that's acting upon the socket. So even though we're weight shifting and we have our center of gravity that's moved over, and as you see in this red line, it's different from the blue line. It's a little more towards the middle of the socket. So now you have this force that's acting on the socket, and we're pushing on the prosthesis, and the prosthesis is trying to help hold us up with a counterforce. There's a lot of pressure inside and on the socket as we're standing on the prosthesis. And this is just in one phase of the gait at one moment. So if we were to try to comprehend all the forces that are occurring on the socket at just one phase, one moment of the gait cycle, we could see that on the left-hand side, we have a downward pressure from loading the prosthesis, but we also have this internal pressure that's pushing out, which is the hydrostatic loading of the limb inside of the socket. So we still have that weight line, the ground reaction force, where we're pushing down on the earth in combination with torque occurring at the bottom of the socket, a torque that we're using to balance ourselves in the socket, and we have an upward pressure that's trying to push and support the amputee as they load the prosthesis. So how do we know that there's a lot of torque occurring on a socket? If we look at this slide, this is actually measured shank torque. So there's a lot of variation in where and how the torque is applied to the pylon. And some of the forces that are acting on the socket, of course, they're going to have a vertical load, and this is your body weight being supported by the prosthesis. Now, as we load the prosthesis, we're going to have total contact or hydrostatic loading, and this is going to try to push the socket out. So you will also have this along with maybe some bony anatomy that you are trying to load, like say the metaphyseal flare, or you might have a bony prominence that's pushing, and these are going to subject the socket to some increased forces. The same can be said for an AK socket. Now, if we look at the AK socket on the right, you can see that there's actually window cutouts. Now, what will happen is the cutouts will move, but then you're going to get increased pressure on where the frame is. So if you have cutouts, the loading is going to be much higher on the frame. And this is partly due to the hydrostatic loading. It's going to want to push out. So if you have less area to distribute the force, you're going to have more pressure. So we talked about the torque on a shank, and you can see that when there's single limb support, there's going to be some rotation occurring as their body progresses over the prosthesis. They're also going to have torque loading because you're trying to balance your weight on the prosthesis within the socket. With the AK socket, you're going to have similar forces acting on it. You're going to have the counter pressures by trying to balance. You're going to have the rotation from the torque, but you're also going to have increased edge pressure and stress risers if you have window cutouts. So if you look at the red circle, this is going to indicate where you're going to have a high tension compression load occurring, where that junction of the lateral and the medial wall will meet with the distal part of the socket. So as much as the amputee is loading the prosthesis, the ground is pushing back against the prosthesis. So through the foot and the components on the bottom, it's going to load the distal end of the socket. And this is because of the ground reaction force. This is why we need to address push through and pull out, because not only do you have the push through from loading, but also the torque can pull out the component. So like the BK socket, the AK socket will also have forces subjected to it. We want to address this with proper component selection and also reinforcing the distal end to prevent push through or pull out, because we will have some additional torque depending on the length, the weight of the patient, and also their activity level and if they have contractures. So if you have a big offset and you have a large contracture, you have a lot of torque occurring, which can actually start to split the socket. So you want to address reinforcing that distal end, especially if you have window cutouts. So when we look at materials and we look at what we're trying to design, a good example are airplane wings. So if we look at the wing on the right, we can see that it's an aluminum wing and the span is quite long. So if we take our reference out the window, we look at it in a static position with the plane on the ground, we could see how flat it is. Now, as we look at the photo just to the left of that, we could see how the wing starts to deflect, and this is during load when it's in the air. So the length is very long. It's a long lever. It's designed to flex that much, and this is under load. So again, if we look at the 787 in comparison, it has a composite wing of carbon fiber. We can see how much it deflects under load and how much it sags when it's not in load. And it's designed to do this. Now again, the lever, the length of the wing is very long. It's longer than the aluminum wing that we're looking at on the right. So when we compare it to what we're doing with a prosthesis or even feet, the lever arms are much smaller. So we're probably not going to get as much flex. It's going to be very stiff, especially when we're using carbon fiber. So some typical materials that are available are braid and tape. When we look at braid, we can see that there are different materials available. Braid is very good because it conforms to most of the shapes that we encounter, cylindrical and also complex undulations. It's not a flat panel. Now if we look at tape, we can also see that there are varying materials available as well. And these are primarily for stiffening or reinforcing. One of the things we did was to try to get a base representation of the materials that we commonly use. And we looked at carbon, we looked at NSP, and we looked at a hybrid of NSP and carbon together. And we did it with a generic shaped BK socket. If we look at the graphs that were generated, we could see the crush curves of the carbon, the Paralex, which is the hybrid, and the NSP. We see that there's initial movement, then it starts to resist, and it goes up and it peaks to where the material fails. Now what we did was we simulated the same with the other materials, the Paralex and the NSP, to the point of failure that the carbon had. And these are the curves that were generated. Some of the results we got showed that the carbon failed by the fiber cracking. Now, similarly, the NSP that we use did not fail, but the resin creased. It allowed the material to move. And this is how we were able to determine that the NSP fiber has 10 times the impact resistance, because it did not actually crack. So if we look at the red curve with the red vertical line, this indicates the amount of energy that the carbon required to fail. For the Paralex, or the hybrid with the NSP and the carbon, again, we'll look at the green curve, and you can see the green curve in the middle where it drops down where it says 20, and that is the amount of energy it took for that material to fail. So the curve is actually greater, the amount of area underneath it is bigger, and it took more energy for it to fail. Let's look at the NSP, the brown curve. You'll see that it is much greater. There's more area underneath that curve, and that's how we determined it takes 10 times the impact strength to make this fiber fail.
This is the NSP, the lighter colored one, the one that showed the pigment in its true color. Okay, I'm balancing. You probably can't see my whole body, but I'm balancing on the socket. Okay? And it's not broken. The fiber won't break. The fiber is extremely tough. The resin will break, but the fiber won't. Now, here's carbon fiber. Same test. Again, I'm not going to hold anything. I'm balancing on the socket, just putting my weight on it to show you. So, carbon fiber. Okay? One more balance job. You probably could hear the cracking sound. And if you look at the socket, you're going to see a white line there. And that is the fiber broken. The socket is now broken in that line.
When we talk about hydrostatic loading, the forces inside are very high. And this can actually rip a socket open. We want to counteract this with circumferential reinforcement around the brim. We refer to this as hoop strength. And this requires just adding reinforcement. When we look at the forces on this page, we can see that there's counteracting forces with torque applied. We can address this with struts, and sometimes it's better to actually apply an I-beam. And the I-beam basically are two surfaces that have a separation gap. Now, the more you increase this gap, it will actually increase the stiffness by a magnitude of 3. So simply adding an extra layer of material, such as Nye glass, if you have two Nye glass separating, for example, NSP tape, the magnitude of stiffness for that NSP tape will increase by a magnitude of 3. So the I-beam that I experimented with is very simple to make. Basically, you take Nye glass stockinette, you run the NSP tape on either side, inside of the stockinette, lengthwise. After you've inserted the NSP tape, then you fold the stockinette in half. Now you have NSP that is separated by 2 layers of Nye glass. Now, since this is contained within the Nye glass stockinette, you can run that along the area where you want to have the reinforcement, as you can see on the picture on the bottom right. This technique makes it easy to apply over trying to have multiple layers of stockinette on the whole model. So you can use this with double stick tape and apply it exactly where you want it. Also, because it's separated by the Nye glass, it will conform as you want to put it along a brim, and you have the shape, for example, like an AK that is undulating and not flat. So as much as the patient wearing the prosthesis is pushing down into the ground, that's how much counterforce is actually being pushed up back through the system of the prosthesis. So we want to make sure we reinforce it to prevent push through and also pull out of that distal component. or the mounting point. So the amount of force that's going through there with the torque, the tension, the compression, there's enough to actually make components fail. So if we look at this, we can see that there's a big stainless steel component on this foot, and it actually made this component fail. So the foot didn't fail, the prosthesis didn't fail, but the actual steel part failed. So there's a lot of force that is going on within this system. We want to plan for making sure that the socket will not fail, and one of the ways that we can prevent push through or pull out is to simply add material above and below the mounting component. For example, if you look at the series of photos here, we've reflected some material back before we actually add on the socket adapter. After we add the socket adapter, we tie it in, and we also add 2 layers of material that is tied into the adapter. So this will help in making sure that the socket is stable and the part does not fail or pull out. So if we look at this picture here, we can see how this component pulled out of the socket. We talked about making sure that the component is tied in and that the socket is reinforced on the bottom with some material. If you look at this picture, what is one of the things you see that might be missing? If you look closely, you can see urethane foam that was applied to the bottom of the socket. And then you can also see that it's lacking a lamination that this component is supposed to be bonded to. It was applied directly over urethane foam. And then there was a lamination that was done for this component onto the foam and the socket. So why is this bad practice? The urethane foam with the component on it, when the weight is applied, there's nothing to stop the component from moving. So what happens is you get micro movement of the component. The micro movement will then start to make the component fail or the lamination fail. And in this case, both of them failed. And so it's not the component's fault, it's actually the socket design and how it was fabricated. So as we look into the layers of this socket, we can see that there's some niglass, there's some carbon, there's some bonding agent, the component, and it's directly on foam. There's no laminated socket that the bonding agent and the component is bonded to. So over time, you can see how this will eventually fail. There has to be something sturdy that everything is bonded to. You're only as good as the base that you start with. Now sometimes we'll have enough layers, but it could be what we inadvertently do. Many times I've seen people laminate where they pour in the resin, they have the vacuum on, and then they untie the bag and quickly squirt in the resin. They don't give the resin time to saturate all the material. So what happens is they actually trap air on the bottom of the socket. And this will prevent the material from saturating, and then you get a weak point. So we want to make sure that we let everything do its job. Let the vacuum suck out the air. Let the vacuum suck the resin down, and let gravity help work all the resin down. This way, you'll be sure to get all the material saturated and not trap air. This will be important as we continue on with this discussion of materials. In simplified terms, carbon fiber is started with a base material. The base material goes through binding, stretching, then it goes through an incinerating process. So it actually gets bonded together through the first incinerating process, and then it goes through a carbonization process where it gets further incinerated. Now, the material that it starts with, the higher the grade of carbon will result. Also, through the incineration process or the carbonizing process, the longer it gets incinerated, the more pure the carbon will get as well. After the incineration process, it goes through the graphitizing process. The graphitizing process essentially is where it's like a heat treatment. This helps it to obtain its high modulus. After the graphitizing process, it then goes through the oxidizing, etching, and sizing coating process. It has to get etched or oxidized, otherwise the coating, or what we call the sizing, will not stick to it. This etching and sizing process is vital because if we tried to laminate raw carbon, our sockets would not work very well. It would basically fall apart because not much resins will stick to raw carbon without the coating or sizing on it. From here, the yarns are then put on bobbins, and then the bobbins are then put into spinning machines. The spinning machines will then gather all the threads. The threads will determine the count of the fibers, which then make up a toe. So depending on how many threads are in a toe, that will then generate the K rating. So for example, you have 3K to 48K, which basically is how many thousands of threads there are in a toe. Generally in prosthetics, we use 12K, so there's 12,000 threads in a toe. Now we also have 6K, which is 6,000 threads in a toe. Now usually the lower the K, the higher the grade rating of the carbon. So after the toes are gathered, they are then again put on bobbins. The bobbins are then used to make either braid or weave, or you can make a tape. So if we look at this picture of carbon fiber braid, we can see that there are some air bubbles in it. Sometimes air bubbles are generated because of an incompatibility with the resin. Also, sometimes you have so many threads, like a 12K carbon, and yet it's all coated, and sometimes that in itself will trap air. Also, it could be if you're using acrylic, if you mix it incorrectly or try to make it cure too fast, it can also outgas. So we talked about carbon fiber. We talked about how it has a coating or sizing. Now when we look at NSP, NSP does not have a coating on it. And so this helps with wet out. So NSP actually does have more impact resistance than carbon, but at the same time it is half as stiff as carbon. When you laminate carbon, carbon right away is stiff. So the nice thing with NSP is you can make it as stiff with certain ways that you lay up the fiber. We talked about IBeam and fiber separation. So when you add more Nye glass in between the NSP fiber, or you separate the NSP fiber more, it gets more stiff. It responds to the IBeam theory of separating those two layers. The more that you separate it, the magnitude of stiffness goes up. So this is nice because now you can design in where you want it to be stiff or where you want it to be more dynamic. Or you can actually have the whole socket be dynamic, depending on how you lay it up. Because NSP is not coated, it actually works with any resin. So you can use polyester, acrylic, or epoxy. But of course, the higher grade your resin, the better the results you'll have. And that's true with any material that you're using. Unlike carbon, NSP is a neutral color, so depending on what pigment you're using, you're going to have that true color of the pigment. You don't have to tint it up or tint it down. Also, if you look at the numbers, NSP is lighter than carbon or fiberglass. NSP is available in different widths and different lengths, 10-foot and 50-foot rolls. It's also been tested under ISO standards for 500 pounds, but the results were inconclusive, and this is in regards to carbon, fiberglass, and the NSP. What had happened was the component that attached to the socket actually broke in many cases. So this is why we came up with a crush test to try to get some numbers that were more relevant and consistent. Also, NSP is available in tape in 1-inch and 3-inch widths, which is 25 or 75 millimeters. Now, NSP works really well with NSP. As long as the fibers are separated, it'll come out very stiff. So one of the things that really makes NSP stand out versus carbon or fiberglass is that NSP actually has a main ingredient that is commonly used in making contact lenses, eye drops, and even implants such as ligament replacements or cartilage replacement. This makes it very body friendly, and that's a nice feature, especially when you're in your lab sanding this material. Carbon has a problem where the material is so small that when you sand it, it actually gets airborne, and that's most of the particles that you see clinging on the walls or on your equipment. The other issue is the small particles will get airborne and you tend to breathe it in if you don't have proper respiratory protection. There was a study that was conducted in China that correlated the relationship between carbon dust, and what they found is that there was a correlation between this carbon fibers that was airborne and breathed in to the lungs and how it started to develop into lung cancer. If you remember the picture of the carbon socket, it had air bubbles that you could see in the picture. Now if you look at this NSP socket, you can see that there are no air bubbles. It's because it's not coated, does not trap air bubbles, and it has really good wet out. So you get all these features of good wet out, no air bubbles, it's body friendly, and can be made as stiff as carbon with the right fiber orientation and fiber separation.
What you're going to see with carbon is you're going to see a dust around the edge, and I want you to pay attention to that dusting effect. That's called fraying, okay? And that's the carbon fibers getting airborne. You can see that dust up in here? Now real quickly, I'm going to put on NSP and do the same grind. You see the fiber, the dust goes more straight out and then goes straight in. So it doesn't get as airborne, it's a heavier dust. But you can see the fiber of the cloth right on this edge that it's making with the NSP. With the carbon, it has it, but it's right at the edge. It's just the inside nylon that's on this lamination that it's holding on. The carbon itself breaks off. The NSP is stronger than carbon, and it doesn't break. It needs to be cut off. So part of the issue is you need a sharp cone. Some practitioners like a fine cone as opposed to a coarse cone. Personally, I can use either cone. Both of these are well cured, by the way. So we're just going to do wet and dry. Very simply, I just take a wet and dry paper and burnish it over. And this is the carbon. We're used to carbon. Okay, and you can see how much fiber is coming off on my hands with carbon. Okay, that black it's a petrochemical. That's what carbon's made out of. So part of the issue has always been how healthy is this for us, particularly when you go home and all your clothes itch and your body itches and stuff like that. It's that fine fiber, that thing I called a minute ago, fraying. When it gets airborne, it's so fine, it's so small, it gets into the pores, and that's why it itches. The NSP, on the other hand, it doesn't fray like that. It puts out a little bit, but it's a heavier molecule because it sticks to the resin and goes down. Now, there's specific weight. NSP is lighter than carbon. As a raw material, it's lighter than carbon. It doesn't need to be heavier. But when you do a lamination, you need to do a lamination relative to the fiber so that the fiber can give you strength. So, unfortunately, you can't feel it. Hopefully, you can see it. You can see how white this is and how this is not. But look at my hands. I'm rubbing on it after I sanded it, and my hands are clean. I'm not getting that black dust that carbon gives you. It's a totally different sense. But that's a totally acceptable smooth edge, and I'm not spending an hour on it. I believe the key to this is sharp paper and a well-cured lamination to make this work.
One of the challenges with NSP when you first use it is try to sand it the same as you would carbon. Now what happens is usually you push too hard and then you burnish off the resin and it gets fuzzy. So it's very important to just change your technique slightly with lighter pressure. It's also really important to make sure that the resin is cured. If it isn't cured, no matter how much you sand it and you try to get a good edge, it'll still get fuzzy because the resin has not hardened completely. So the issue with a rubber arbor is when you apply too much pressure, the rubber arbor will start to build up heat. One way around this is you can get a diamond sanding cone. Because it is metal, it acts as a heat sink. So you can still apply pressure and the metal will actually absorb the heat and it'll still cut with the diamond coating on it. The nice thing about these diamond coated sanding cones is that if it gums up, you just put it in the oven and it will loosen what's on it and you can peel it off and it's good as new. Durability has been seen in this socket, which was made by David Littig. It was about 4 years old at the time of this picture, and he commented that this leg had no stress fractures that were visible, even though this leg was used by a construction worker. Ultra 6 carbon is a higher grade carbon than is used in the industry standard of the 12K carbon that you normally would get. So yes, you do have less strand count. You have 6,000 strands versus 12,000 strands, but you get a higher grade carbon. So the strength is about the same. Now the one thing you will get out of the 6K versus the 12K is it will lay on your cast smoother. Also when you laminate it, it will lay flatter. The nice thing too is because there are less strands, there's less coating to deal with. Also, with that, you'll have less trapped air. Our Ultra 6 carbon has been designed to lay up flatter, and it's in the manufacturing process that makes it different. So it is available in 3 inches, up to 10-inch widths, and at 10 feet and 50-foot lengths. Our carbon tape is an Ultra 6 carbon tape, so there are 6,000 strands in a toe. This makes it very strong compared to a 12K tape. And as you can see, it comes in different widths and different lengths. Now, if you recall the testing graph of the Paralex, remember that the curve looked exactly the same as carbon, but it took more energy to make it fail. So this is a combination of weaving the NSP and the carbon together, and you get your IBeam stiffness from both of them. The nice thing too is you'll have the impact resistance of the NSP, but you have the stiffness of the carbon. As you can see, it comes in different widths and different lengths. We've had really good feedback on different applications, such as this application with an articulating AFO. It has good stiffness and good fatigue strength. We do provide a 12K carbon, and the nice thing about our carbon is the grade of carbon is higher than your standard carbon. You can tell by the coating that's on it or the sizing. So if you take your braid and you hold it out, you'll notice sometimes it's very stiff. If you take ours, it's not going to be as stiff because the carbon grade is better. And this is one way to check. So if you want a 12K carbon, we have 12K carbon, and also it comes in different widths, 3 to 10 inches, and different lengths.